Okay, now we will talk about a very important concept in electrostatics, which is the concept of the electric field. This might be a bit hard to understand, but if you just focus a bit and follow me, we will be able to make you understand what is the electric field, how you define it, how you find its direction, and what is the relation between the electric field and the electric force. Now, electric forces are an example of what we call field forces. A field force is a force that can act through space. In other words, you don't need to bring the objects into physical contacts so that they exchange this force. Now, this is obviously is the case with electrostatic force, as we have seen. When you have two charges, these two charges will exchange a force even when they are far apart. They don't need to come in touch for them to interact, to exchange force. Now, another example of a field force is gravitation. I mean, the Earth attracts the Moon even that it's 300,000 kilometers away. And also the Sun attracts all the planets, although they are millions of kilometers away by gravity. So gravity is also an example of field force. Now, let's go back to the electrostatic force. We say that in a region of space around a charged object, there exists an electric field. So this is how we introduce the idea of the electric field. You have a charged object. Now the space around that charged object has an electric field in it. Now the charge that creates this electric field, we call it the source charge. So this is an important thing to keep in mind, the source charge, the charge that generates that field. If we are to show it this way, now in any region in space is different before and after you introduce a charge. So in this region of space, for example, before you bring this charge, there is nothing there. After you bring this charge, this area surrounding the charge now is electrified, if you like to call it this way, because there is now an electric field generated by this source charge. So the presence of this source charge in a region of space generates something in that space that did not exist before. And this thing is called the electric field of this source charge. Okay? So this is the idea of the electric field. Now, how do you know that there is an electric field there? Well, to test that electric field, you need to bring in a tester. What is that tester? We call it a test charge. Now, a test charge is a theoretical object, actually, a theoretical idea. And usually it's a small charge, small so that it doesn't disturb the source charge. That's the only requirement. Now, when you bring this into a region where a field exists by another source charge, then this will feel a force. So this is why we call it a test charge, because it is the tool that you use to test for the presence of a field in some region. Okay? So this is the test charge, and this is the charge that tests for you that there is electric field generated by this in this space. Now, how we define the electric field, if you want to define it quantitatively, then how we would define the electric field? We say that we define the electric field at a given point in space as follows. We say you put a test charge there and you measure the force acting on that test charge. This is the force vector, so it has a magnitude and direction, and you divide it by the test charge. Now, this result gives you the magnitude and direction of the electric field at that particular point. Note that this is a vector equation, and Q naught that appears here appears with its sign. Okay, so this is important. So this is generally how you define the electric field at a given region. You just put a test charge there, find the force acting on that test charge, divide it by the test charge with its sign. The result is a vector whose magnitude and direction give you the magnitude and direction of the electric field at that particular point. Now that electric field is not generated by the test charge, as we have just seen. Remember? The electric field in this space is generated by the source charge. The test charge just acts as a tester. It tests it. So the field actually is independent of whether you have this test charge or not. It is there always once the source charge is there. Now, so this is again an emphasis of this. The existence of an electric field in space is a property of the source charge. The presence of the test charge is not necessary for the field to exist. It is just a tool, the test charge, to test that electric field. So this is the definition of the electric field. Now, how we can find the electric field of a source charge everywhere in space? You know, as we have seen, when you bring a charge into space, then around that source charge there is an electric field. So, and this electric field might vary from a point to a point. It will have different magnitudes. It will have different directions at different points. So how we define it? First of all, it is a vector, as we have just seen. So we must find a way of defining its magnitude or fixing its magnitude and its direction at all points in the space surrounding the source that created this electric field. And how we do that? Well, that is how we find the electric field vector at different points in space. What we do is the following. We assume that we take now a positive test charge. So this is important, especially when you want to fix the direction of the electric field. You have to take a positive test charge. And the electric field vector at a given point in space is the force on a positive test charge divided by that test charge. So this is how you define the electric field vector at a given point in space. Okay, you take a positive test charge, you put it at that point in space, you find the force on it, divide it by the test charge, you find the electric field vector, magnitude and direction. Okay, since this is positive, then E in this case and F are in the same direction. So to make sure that we understand what does this mean and how we find the direction of the electric field at a given point, this is an example. Consider this is a source charge and I want to find the electric magnitude of the electric field vector at this point in space, at a point here. Okay, I bring in a positive test charge and I put it here. Now what will be the direction of the force on that positive charge? Well, for this particular example, the source charge is also positive. I have here a positive charge, so the electric field, according to the electric force, according to the Coulomb's law, will be away from this charge in this direction. Therefore, this is also the direction of the electric field vector at this particular point. If I want to find the electric field here, I take this positive charge, put it here. In this case, the electric field will be the electric force on this test charge will be in this direction, this positive test charge, and therefore this is the direction of the electric field at this point. I want to find it here, the direction, you take this test charge, bring it here, and find, okay, what will be the direction of the force on this charge by the source charge? It will be in this direction. Okay, then this is the direction of the electric field here, and so on and so forth. Now, since the electric field is force divided by charge, then its units are newtons per coulomb. The SI units are newtons per coulomb. Now, generally, if you don't see the positive charge immediately, or you want to, you are not sure if there is an electric field in a region, or you want to check if there is an electric field somewhere in space, then when you actually, you can say, okay, I have electric field in a region in space. If when I bring a test charge there, it will feel a force. In this case, that space is not really innocent free space. No, there is something in that space, which is the electric field. Okay, so this is how we can think of the presence, or we can check the presence of electric field. Now let's do an example here to make sure that we understand how we find the direction of the electric field. So this is our source charge here, and we take it as positive, and I want to find the direction of the electric field at a point P here, for example. What I do, I bring, because I'm checking now the direction of the electric field at a given point, I must use a positive test charge. So I bring in a positive test charge Q naught. So I put it here, and then this is positive, the source charge is positive. The force on this Q naught is in this direction. Therefore, the direction of the field in this case of this point source charge at this point P is here. Here I removed the charge here because I can define the field here even in the absence of this point charge. So I know now that I have a field at this charge, at this point P here, and this field is directed in this direction. This electric field is directed in this direction. Now, in the second example, the source charge is negative. So I have a charge which is minus Q, and I'm placing it here. I want to find the direction of the electric field at point P here. What I do, I bring in a positive test charge. I bring in a positive test charge, I put it here, and then find what is the direction of the force by this minus Q on this positive test charge. It is, this is along this arrow. Then the direction of the electric field due to this minus Q at this P is this. Okay, so this is how you find the direction of the electric field generated by any source charge at any point in space. Now, the source charge does not need to be always a point charge. It can be charges distributed over a surface, a volume, a line, as we will see later, but the idea is always the same. So the direction of the electric field at any point in space, to find it, you put a test charge there, or you imagine a test charge there, find what is the direction of the force, and that test charge would be positive if you want to find the direction of the field. Find what is the direction of the force on that positive test charge. That will be the direction of the electric field at that particular point. Now, the force depends, of course. To have a force, you need, to have a force, you need a test charge. But the field exists even in the absence of that force charge, of that test charge. So this is something that you have to keep in mind.